Hi, so today I want to talk about something, is this working? I don't know, yeah. Something extremely topical, so the future of intelligence. I don't know if you guys have been following in the news, but there's this current battle between the London-based company DeepMind, Google DeepMind, and Lee Sedol, one of the all-time great Go players, I guess coming towards the end of his career, but still one of the best in the world, out in Korea at the moment. And I just wanted to sort of talk a little bit about it. In fact, the DeepMind guys were at UCL when we were there, so we know them a little bit. I had lunch with one of the co-founders yesterday, and I've got to be very careful not to reveal any of the non-public stuff today. So if I sort of stutter, you can use your intuition to guess, then it's something private. But this is, of course, not by any means the first in the human versus machine contests. So I just wanted to set this in a little bit of historical context. The very first victory of a computer over humans was actually in noughts and crosses. So the game had obviously been solved way, way before this. But in 1952, a guy called A.S. Douglas at Cambridge was the first to ever actually code it into a computer. So the only thing that was stopping computers beating humans at this point was really computers existing at all. After that, it took quite a while for the next marker to fall. So in 1995, a computer first beat a human at drafts, an algorithm called Chinook. Actually, this is maybe a little bit of a kind of underestimate, because there was, in 1994, the champion was this guy, Tinsley, who was an incredible drafts player. He'd, over a 45-year career, he lost about 7 games. Unfortunately, he had to retire in his match against Chinook through illness. He died 7 months later, and the person who took over was just nowhere near as good. And so we lost this one maybe a little bit before we needed to. Then, obviously, IBM's Deep Blue was very, very famous, beating Kasparov in 1997. Probably the next big human versus computer was Jeopardy, the IBM Watson taking on the two best Jeopardy players of all time and beating them. And then in the kind of relatively recent past, there was the DeepMind Atari, so taking on or challenging humans, a single algorithm challenging humans, some of the best human players, at 50 different games and playing them all and taking them on. And it won, at least at the time of publishing, about, I think, 50% of those. It was just clearly dominant. Another 20% was about the same as humans, and then the rest were below humans. And then finally, we're in this 2016 era of humans taking on, computers taking on Go. So what's the actual challenge? So back in sort of September last year, these guys, DeepMind, who specialize in artificial intelligence, challenged the European champion to a game of Go. To a series of games of Go. This is Fan Hui here. So the European champion sounds like they'd be very good at Go, and on an objective scale, they are, but they're a long, long way beneath the top players in Asia. So this guy actually, he started playing at 12. He relocated from China because he realized he was never going to be a top Chinese professional, and came here and set up in France. And he's the reason why the French team are the best in Europe at Go. He's just single-handedly just lifted their entire Go program. So we should probably try in England, we should probably try and figure out maybe get Lee after he loses all his confidence to come over here. But the algorithm, smashed him. It's 5-0. At least in the formal games. There were another 5 informal games, of which he won 2. So There was sort of, they estimated that, they probably would beat this guy about 80% of the time with their existing algorithm. But of course, that was 6 months ago. And they've had 6 months to progress. And we know computers do an extreme, or very smart people working with very powerful computers with Larry Page's open wallet can do really great things. So where are they up to now? So I just want to sort of explain briefly why AlphaGo is different. What is it that makes it better than any other algorithm we've had previously? So if you look at chess, and you think about just in a very abstract fashion, you have lots of pieces on the board, and at any one point, it turns out there's about 19 different moves that you can make. So you can imagine, and if we'd drawn this out properly, there should be 19 branches here. And then off those, there's 19 more branches. And off those, there's 19 more branches. Now that is fundamentally not possible to solve in any relevant time scale just by going down all of the branches and figuring out the best possible course of action. But with some very handcrafted heuristics, they managed to make this problem solvable. And that's how IBM's Deep Blue essentially won. So it kind of tracks down all of these branches and searches them out and figures out the best outcome. And IBM puts in rules like don't lose your king, don't let your queen get taken, those kind of things, which let it chop off chunks of these branches and not have to do all of them. The problem with Go is that instead of 19 branches at every point, you have about 200. And so for 200 from the first one, and then 200 off every one of those 200, and 200. So even these rules, this way of doing it, where you kind of searched down most of the branches and got some ideas, was just completely infeasible. And this was fundamentally, the best algorithms that we had, what they would do, they were called Monte Carlo Treesearch. So they would kind of start here and only take one branch, and then do that again and do another set, and do that as many times as was possible to compute in the time they had allowed, average over all those answers, and then try and steer the course on that. But they were never even close to a professional level. So tree search, this idea of just plowing down the tree is impossible in Go. So what did DeepMind do differently? Well, they introduced this idea of having two neural networks that would basically steer the search. So they call them the policy network and the value network. And essentially, the policy neural network was trained on what humans tend to do in Go. So they got tons and tons and tons of Go games, trained a neural network, just a kind of algorithm so the underlying structure of a neural network sort of mimics the way we think the human brain works. So we call it a neural network, but it's really fundamentally just kind of a maths algorithm. And so they got this policy network, they called, and they trained it on loads and loads of games, and then got it to predict the moves. And so that allows it to just get rid of a ton of, probably they don't, the details are a bit more complex than this, and they probably don't just take the one option that their algorithm predicts. But you can imagine if you have 200 of those branches, and I can tell you roughly the 2 or 3 moves that the opponent's likely to make, I can really narrow the number of searches I have to do. And then the second thing they did was this value network. So another problem with Go is, let's say I can even compute. So a Go game might be 150, 200 moves. And let's say I can compute all of those 200 by 200 by 200 branches, even just 10 steps in, right? That gets me to a board position. What the hell does that mean? How do I interpret that board position? And I don't know if any of you have actually watched the coverage today, but it takes an incredible level of Go skill to look at a board and be oh, so black's got that part, white's got that part, and they just count it. The guys, I would check it out. It's a weird skill to watch. The way they can there's 65, there's 20 stones there, and 10 stones there, and 5 stones there. But if you want to build that into an algorithm, you need this incredibly high level of Go skill just to just to even figure out whether this is a board position that you want. Like, I cannot tell. Like, everything they do means absolutely nothing to me. And I just can't imagine how you'd code that into an algorithm. But they don't. They just take a neural network, they throw a ton of board positions at it, they know who won or lost the game, and so by just training it on that, they can like figure out. I mean, it's really just, if you think of like photo recognition, where you're recognizing like a bike or a cat or a dog, they're just treating black and white stones as pixels, and just training the Go algorithm to recognize winning and losing as two separate, like, you know, like cat and dog. So that lets them, you know, so the policy network can predict what the opponent's going to do. The value network can understand like whether a board position is good or bad for the algorithm. And then they do this tree search. So they still have an element of like plowing down and just doing incredibly complicated, tons and tons of calculations at the end. But because they've steered it with these two neural networks, the actual amount of computation they need to do to get the performance is like much, much less. And then, of course, they're Google, or at least, they are Google now. And so they have incredible hardware to do that as well. So, I mean, there is a debate, actually, how much of their performance is even just due to having Google's hardware and how much is algorithmic. And it seems like it's both, but it is very clearly not just one and not just other. My clicker seems to have stopped. Oh, no, sorry, it's doing the... I was animating the tree search. That took me like 5 minutes to do. I just skipped over it. All right. So this is it. This is really the secret to AlphaGo's incredible performance, is really great hardware, incredibly smart programmers doing the tree search at the bottom, but steered by these very, very cleverly built and cleverly trained neural networks to reduce the computation time. And, you know, this starts to look a little bit scarier as well, because this generalizes a bit more, right? In the sense that, like, the way, if you listen to how really good Go players talk about Go, they don't really say, like, I put my square there or my thing there because I know that this will happen. Like in some simple cases, they do that. But often it's like, well, I felt like this part of the territory was vulnerable, and if I did this, I could kind of shore up the defense. And it's very intuitive. And like, so that was how humans played it, and that was kind of why we thought that Deep Blue beating Kasparov at chess wasn't a big deal, because it was very like kind of mundane and sort of cranking through combinations and not very intuitive and not very intelligent. These guys up here start to look like intuition. They start to look like our kind of the things that we would think of as intelligence. So then we decided we wanted to try and predict the result. So this is actually from before any of the anything took place. We thought we'd just kind of talk you through what we thought was important. So the first question is, how good is Lee relative to Fan Hui? So Fan Hui was beaten in the first one 5-0. How good is this new guy, Lee Sedol? And the best way of assessing this is really there are like these ELO ratings like in chess. So Lee is a 3,500 on this scale, and Fan is a 3,000. And that 500-point gap means that Lee will probably beat Fan like 95% of the time, if not more. So he's really, really much better. Like DeepMind have said repeatedly that they don't think the original version of their algorithm would have had any chance against Lee. So there we go. So that's kind of the original algorithm. They assessed to be about 3,200. Fan was at 3,000 and Lee was at 3,500. We want to start our prediction by asking about the base rate. So like one of the things that's come out of psychology is humans are terrible predictors, but the way we can make ourselves the best possible predictors is starting from a reasonably good historical estimate and then adjusting for special circumstances based on that. If you adjust for the special circumstances first and then tweak with a base rate, you just tend to be way off. There's nothing really fundamentally that makes it obvious that one way is better than the other, except that psychologists have tested it over and over again, and this way is better. So if we look at these kind of like human versus machine challenges, we see that actually in sort of 75% of cases, companies have challenged too early. They, like Deep Blue lost to Kasparov the first time. The guys lost at drafts. There's been another ton of challenges that nobody even talks about because it was just so rubbish that no one publicized it. So even in these very public challenges where everyone in the world knows about it, it's still plausible that computers lose. Now, knowing Demis and Shane, the like DeepMind founders, they're pretty smart. Like, I would be very surprised if they put themselves in a position to lose publicly like this. But of course, they're not necessarily in charge of everything. There may be other external pressures that we have to think about when we're estimating from the outside. So we sort of scored this one, the historical, in favor of Lee. If you looked at what Go experts were saying, there was just no possible way Lee could lose. So probably 95% of them were just like, it's going to be an absolute whitewash. AlphaGo might get a game if it's lucky, but there's no chance. The problem is that very, very strong domain experts tend to be terrible predictors when new information comes in. So this is another one of those kind of psychology results, a guy called Tetlock. He talks about hedgehogs who know one thing very well and foxes who know many things, a little bit about many things. So we think that probably in making our estimate, we're not going to take this too seriously because these guys have no sense of what AI is capable of and the progress in AI. Very good at Go, but this is a new kind of domain of knowledge, and we don't think that there's too much useful to be gleaned from their opinion. Finally, there's the kind of, well, AlphaGo is perhaps an overstatement, but the sort of AI/Go experts. So the people who know quite a lot about Go and quite a lot about artificial intelligence. And these guys all scored it about 50-50. They were kind of unsure. The other thing we need, so we have a sense of how big the gap is between Lee and Fan. We have a sense of a base rate to start from. So it's not plausible, really, looking at those historical results, that it's going to be clearly to AlphaGo or clearly to Lee Sedol, right? In both cases, you can make arguments that either would lose. What we want to know now is how much progress in the algorithm is likely in the time they had available. This is an interesting one because it's very hard to assess, right? Behind closed doors, with all of Google's money, with all of Google's people, what can they really do? The thing that we used to predict this was the fact that human-like performance is probably not that big a marker. So, if you think about the absolute scale of Go ability or chess ability or anything like that, humanity exists as a point on it, but as far as the universe is concerned, it doesn't care, right? It'll just breeze past us. And so what we did was take DeepMind's ability to, build this algorithm over the last 18 months and just extrapolate it out for another 6 months. And that told us that there was about 400, we predicted that there'd be about 400 ELO points that could be gained in that time. They'd kind of gone from the other algorithm was at 2,000, the next best algorithm. They'd got up to 3,200 in 18 months. Okay, let's give them another 400 for that 6 months. And then, of course, when something gets this public, people are going to put more money in. And so there will be more hardware available to them. They'll be able to do more computations, and actually the rules changed slightly, which gave them a bit more time to work. But looking very carefully at the paper they published, it's clear that there's diminishing returns with hardware. So kind of the performance started to tweak, started to slow down, even though they were dramatically increasing the hardware. And so from that, we gave them about another 100 ELO points. So when you put all that together, you come up with these estimates. So that shouldn't be original AlphaGo. So original AlphaGo was 3,200. We gave them 400 points from algorithm, 100 points from hardware. So we estimated that upgraded AlphaGo would have about 3,700 ELO points. And Lee Sedol sits here in the middle with 3,500. So if you take this kind of difference here and convert it into a win-loss ratio, you'd expect upgraded AlphaGo to beat Lee Sedol 4-1. Then, of course, with the base rate, with our base rate estimate, we're probably going to hedge down a bit because it seemed like that was slightly in Lee's favor. But the current result, 2-0 to AlphaGo, suggests maybe even that isn't necessary. So we'll kind of see where this goes. Of course, so there's a day break tomorrow and then another couple of games. But it is only, DeepMind are only one match away from confining, human brains to the dustbin on basically every task, every game that we had available to us. So what does this actually mean? Like how much? I guess the big question around artificial intelligence is when is it going to supersede human intelligence, right? I don't think there's many people now that would really genuinely question if that's going to happen. It is much more a question of when. And so how much should we adjust our timelines based on this result? So there are, the DeepMind guys like to publicize this number of this was at least 10 years away, according to some experts. Now, that is true that some of the biggest experts in the world have said that, but other experts have said quite a lot less. And their coverage has tended to focus on the ones that said it was very far away, rather than the ones who said it was much closer, which of course is exactly what I would do in that situation. But we have to sort of factor that out a little bit. So probably what we can say is that it's moved the time horizons forward by a couple of years. But the truth is that the algorithm they developed for AlphaGo is really much more specific to Go than the algorithm they developed for the Atari games was. So the Atari games algorithm was playing 50, 60 different games, exactly the same algorithm training on all of them. The AlphaGo one really is, real incredible technical achievement, but very somewhat handcrafted for Go. So I think probably what we can learn from this is not so much in the domain of general intelligence. The Atari result taught us that neural networks are incredibly general for solving many tasks. The AlphaGo result it tells us that by chaining together, using neural networks in combination, by using them with other completely familiar techniques, we can achieve things that are incredibly powerful and can make performance on tasks appear to increase extremely dramatically. So then one last thing is that if you would actually like to hear two genuine experts debate this, at Strata Hadoop in May and early June, I'm going to be hosting a panel with Stuart Russell and Jan Tallinn to debate the future of intelligence. So I'm extremely excited to listen to this. And if you're interested, Angie has put a discount code up here for ASI people. So with that, thank you very much for your attention, and I'll hand back over to Angie.